Okay, consider that we have a charge conducting sphere. This is a solid sphere. It's conducting, made out of conducting material, metal. And we're going to charge it, place some charge on this conducting sphere. Examine what happens. Uh, because this is made out of conducting material, we know that the material itself has a lot of free electrons or free charges that will be able to move freely within the material in response to an electric field if it is present. Now, consider this. Let's suppose that I have within this material an electric field in this direction, E. Imagine if I had a whole bunch of electrons within this electric field. What's going to happen to this electron? Well, the electrons, of course, are going to feel a force. Which way will that force be? Well, because the electrons are negatively charged, the electrons will move in this direction, feel a force in that direction. And so inside of this conducting material, the result of this electric field will be a lot of electrons moving towards the left. What effect will this migration of electrons have on the existing electric field? Well, if you just look at these electrons themselves, they are going to produce an electric field all by themselves. Just these electrons will produce an electric field in this direction. The resulting electric field within this material will be the sum of these two electric fields, the existing electric field together with the electric field caused by the migration of electrons. The overall effect is that the electric field in this material would be reduced. Well, if the electric field is reduced, nevertheless there is an electric field, more electrons will migrate. The equilibrium configuration will occur. That is, electrons will stop moving when, of course, the electric field inside of the material is equal to 0. And so the condition of electrostatic equilibrium means that within this conducting material, the electric field is equal to 0. That's within the conducting material. The electric field is equal to 0. The charges within the conducting material will redistribute in such a manner that the new redistribution of charges will cancel any electric field that is present. So the electric field within a conducting material is always equal to 0. Well, what effect does that have on the charges of this charge of this sphere? Well, let's apply Gauss's law to this charge conducting sphere of radius r. And I'm going to draw a Gaussian surface, or use a Gaussian surface, which is just slightly, much more than I can draw, but slightly less than big R. Here's my Gaussian surface, and here's my infinitesimal area on the Gaussian surface. Here's the delta A as such. Now, keep in mind that since this Gaussian surface exists within the conducting material itself, that the electric field on the Gaussian surface is equal to 0. Well, if the electric field is equal to 0 everywhere inside this conducting material, the flux, the electric flux through the Gaussian surface is equal to 0. What that means is that the charge enclosed within the Gaussian surface must be equal to 0 by Gauss's law. So what about the charge? We charge this sphere. What happens to this charge? Well, what this means is that the Q that exists on this must reside on the surface of the sphere and nowhere else. So whenever you charge a conducting material, the charge will exist on the surface of the material, not within the material. If it's a non-conducting material, then we can embed charges within the material. We can have a uniformly charged non-conducting sphere. However, for a conducting sphere, If we charge it, the charge will reside on the surface, only on the surface. Another way of looking at this is the charges that that you deposit on a conducting material are free to move, and so what they're going to try to do is get as far away as possible from each other. They're going to repel each other, get far away as possible, and getting far away as possible from each other means, in the case of a sphere, they're going to exist on the surface of the sphere. So that's something important to remember. So what it means is that when you read a problem, when you encounter a problem, it's very important that you understand whether that material, that charged object, is conducting or non-conducting. It has great ramifications to the way the charge is distributed.